Overspeed is one of the most destructive conditions for any diesel engine. When RPM goes beyond design limits, it can cause catastrophic failure within seconds, from broken connecting rods to total crankcase explosions. That's why overspeed protection is not optional. Every auxiliary engine must prove it can defend itself before it ever reaches that danger zone. This is why we carry out overspeed protection tests regularly, not just as good practice, but because rules and inspections require it. It's a mandatory check built into both class regulations and company procedures. Today, I'll walk you through how we test the overspeed of a Wartsila auxiliary engine with ESM-20 safety system. Let's probe it on.
I saw the name immediately. I knew this is the guy. Again.
See you next time, mate.
See you.
Good
Thank you
luck.
very much.
Bye.
First, let's put DG1 to manual mode. Here on board, our Wartsila auxiliary engine is fitted with the Engine Safety Module, or ESM-20. This module is the electronic brain, continuously monitoring RPM, oil pressure, and temperatures. If overspeed is detected, it sends an immediate shutdown command, cutting fuel, tripping the engine, and preventing mechanical destruction. In this ProbeTips, I'll walk you through how we test that function in practice. We start by following Wartsila's procedures for testing the overspeed shutdown function. The tool for this job is the Wartsila Speed Simulator, a frequency generator that sends RPM signal in place of the engine's speed sensors. When the frequency rises 115% above nominal speed 900 RPM, the ESM should trigger an overspeed shutdown. Step 1. Disconnect the primary speed sensor ST173 from input X13-2 on the ESM. Connect the Wartsila Speed Simulator to this ESM input. Along with 24-volt supply and ground from X13-1 and X13-3. Step 2. Slowly increase the simulated engine speed by turning the knob. But here's what happened. The stop solenoids activated before reaching overspeed. Shutdown occurred at only 383 revolutions per minute, far below the 900 revolutions per minute nominal speed. Why? This time I turned down the speed simulator to minimum. I recalled it last time that we did it while the engine is running.
Tingnan mo, ilalagay natin sa normal yung test. Normal lang. Tapos, assembly tayo. Nagagana yan. Pero kapag nakatest mo, may engine.
Here's where theory meets reality. The stop solenoids activated at just 383 revolutions per minute, well below our target. Why? Because this auxiliary engine has no lube oil standby pump. Any simulated speed above 300 RPM tricks the system into thinking the engine is running without proper lubrication. Low pressure protection kicks in first. Unlike the Wartsila main engine on board, with lube oil standby pump. Here, the attached lube oil pump is driven only during engine rotation. So once simulated speed goes above 300 RPM with no oil pressure, the low lube oil shutdown is triggered. To verify, I probed the simulator output with a multimeter in frequency mode. At minimum, the frequency reading was valid. To reset the ESM-20 shutdown alarms, reconnect the speed sensor to the ESM input. And press the reset button. Once alarms cleared, we will repeat steps 1 and 2. This time we will reconnect the multimeter to the speed simulator. The minimum reading showed 7.71 Hz. Again, the stop solenoid tripped under low lube oil pressure shutdown. Even so, we will continue increasing the simulated speed until the ESM registered an overspeed shutdown at 115% of the set point. At this point, a speed differential fail alarm also appeared since the primary sensor ST173 was reading 332 RPM, while the secondary sensor ST174 showed 0 because the engine was not running. That confirms overspeed shutdown logic is active and functional. I think we should put it in test mode, that is to enable stop/shutdown override. Reset the overspeed trip by pushing the reset button. Before continuing, I noticed an issue. Bus 1 supply showed no power indication and earth fault monitoring was inactive, off position. I adjusted the earth fault relay threshold to 10 kilo ohms and extended the time delay from 4 seconds to 16 seconds. We will revert to the bus 1 supply later. The procedure clearly states, do not perform on a running engine. But this time we'll do it to tackle the elephant in the engine room. Why did shutdown activate early? So let's probe it on with the engine running. One. Disconnect the primary speed sensor ST173 from input X13-2 on the ESM. Connect the Wartsila speed simulator to this ESM input along with 24-volt supply and ground from X13-1 and X13-3. With the stop shutdown override switch set from normal to test mode, the system is now in test condition. This disables actual shutdown functions while maintaining alarm monitoring, critical for testing without stopping a running engine. Next, connect the multimeter to monitor the frequency generated by the simulator. Now, let's start the engine from the local control panel. And allow it to reach rated speed 900 RPM. Two, slowly increase the simulated engine speed by turning the knob. With the engine actually running at 900 RPM, ST174 now reads a real speed signal. This eliminates the speed differential fault we saw earlier. Now we can see if overspeed protection truly activates at the design set point. That confirms the overspeed shutdown. Three, verify that all overspeed safety actions are performed by the ESM when reaching overspeed. Four, disconnect the speed simulator from the ESM input X13. 5. Reconnect the speed sensor ST173 to ESM input X30. Six, reset the overspeed trip by pushing the reset button. The same procedure is repeated for the secondary speed sensor ST174 by following the exact steps used for ST173. By running this test with the engine running, the logic becomes clear. In the previous case, the shutdown happened early because low lube oil pressure protection was triggered at simulated RPM above 300 since the attached pump wasn't running. But with the engine actually rotating and oil pressure maintained, the overspeed trip can be verified correctly without interference from other shutdown conditions.
BMS ko na. BMS mode.
May window dito na nilagay ka. Ano naglagay nun? I-reset pa. Reset.
Naka-block pa doon.
Hindi, nilagay mo na remote ka na.
After the overspeed test, a few alarms remained on the ESM. These appeared to be linked to the bus 1 power fail issue we noted earlier. To confirm, we checked the bus 1 fuse. It was blown. Tracing back, the cause was a wrong connection to the X11:1-2 inputs during our test setup. These terminals belong to the bus 1 24-volt supply. That's it, bus 1 power supply is back online. At the local control panel, all alarms cleared. The same was confirmed at the integrated automation system.
Malinis na.
Fuse. Ito, sa maling
If you're wondering how the stop shutdown override switch is actually wired, let's take a closer look. This feature wasn't part of the original installation. It was added later as a retrofit, primarily to facilitate overspeed testing. According to the Wartsila 20 engine O&M manual, which outlines ESM-20 functionality, the stop/shutdown override can be manually activated in critical situations to keep the engine running, even when certain shutdown conditions are met. The switch uses normally open contacts, terminals 3 and 4, wired directly to the ESM input at X16:9 and X16:10. In its default open position, all automatic shutdown functions remain active, but when switched to override, most automatic shutdowns are suppressed, except for a few critical protections: overspeed shutdowns 1 and 2, always active; external shutdown 4, emergency stop, depending on configuration; low lube oil pressure shutdown; and engine shutdown 1, oil mist detection. Alarms will still be triggered, but the engine won't trip. This allows you to simulate faults, test shutdown logic, and verify the safety check without the engine being forced to stop during each test.